Hi, I'm Will Trickett, and I've come to have a look at the new use of the energy in this river to make electricity. A new turbine has been built to produce green and renewable electricity here at Kingston Mill. It's also a story about two remarkable men, a doctor and an engineer, who have got together to build the most beautiful water-driven turbine that I have ever seen. We are now going to go and meet Dr. Rupert Gabriel, the man that made all of this happen. Hi there, good morning.
Hello.
My name's Will Trickett. I was wondering, would it be possible to see Dr. Gabriel?
Hi. Will Trickett's here to see you.
Hi there,
How
I'm
do you
Will
do?
Trickett, good morning.
Rupert Gabriel.
Hi there.
Nice to meet you.
Oh, thank you very much, nice to meet you too. I'm quite excited. I hear that you're building a massive turbine on the river.
We are building a hydroelectric turbine to generate electricity, as we use quite a lot in the clinic.
Yes.
It seemed like a good idea to generate some too.
Yeah. Whereabouts are you going to put it?
Well, we'd like to have put a turbine in Wiltshire, obviously, because it's closer.
Yes.
But they're diverting the river for a big project with the canals and so on at Sellington.
Oh, I see.
So that wasn't really a long-term option.
Mm-hmm.
But Alec Moulton in Bradford and Avon had a site, an old mill site that was, available, if you like, and
Cool.
so that's the one we're looking at.
Wow. And why have you chosen that spot? Is it a particularly good part of the river, or just because it was available?
Well, it's available, and there are relatively few free sites, but it is the River Avon,
Yes.
so there's plenty of water.
Yes. Even in the summer?
It's actually less flow in the summer, but a higher head. One of the challenges of most sites on the Avon is that the head, or the distance the water drops, created by the weir, is only a couple of metres or so.
Okay.
But there's a high volume.
Okay. Do you have to use a particular type of generator to make the most of that sort of situation?
It has to be big, basically, to manage a large flow.
What sort of size?
Well, the one we're building is going to weigh about 12 tonnes altogether, with a runner that's over a metre in diameter.
That sounds like quite a good bit of equipment.
Yeah.
And what's the... so if you're putting this in Bradford on Avon, I kind of assume you're joining up to the grid. And then at this end of the wire, what's your specific use?
We use lots of electrical equipment in our medical and aesthetic practice. Principally lasers, which are quite energy hungry. They use about 5 kilowatts or so for a big arc lamp, which then excites the laser and creates the laser beam. So, it seemed then, if we were using these energy hungry devices, it'd be good to generate some. Yes.
Well, if you're building a generator of that sort of size to power your equipment here, I mean, would that make you one of the first or the only company that's generating your own power to be green in laser technology?
Possibly. I mean, there are plenty of hydroelectric generators and there are plenty of clinics, but having a direct link between the two is pretty unusual, I think.
Yes.
Yeah.
I bet you're quite proud of that, aren't you?
I am. Well, would you like to go and see it?
I would love to come and see it, yes.
Okay,
That would be
let's go.
great. Oh, thank you very much. So Rupert, today's the day. We're going to have a look at the site of the turbine installation
Absolutely, from the air.
in this machine.
Absolutely.
Can you tell me what it is?
This is a P&M Quick microlight, a 100 horsepower engine, and it cruises 2 up, obviously.
Yes.
It's about 80 miles an hour.
Fantastic. And what sort of range does a machine like this have?
This will go 450 miles on a tank full.
And what's the furthest journey you've ever taken this
We've
on?
flown to France,
Oh, that's a big day out.
or the Scilly Isles.
Crikey.
So, yeah.
Yeah, that must be fun.
Yeah.
Well, today, how far are we going? I know we're going in that direction,
Yeah.
but...
We're only going about, say, 10 miles. From here at Yatesbury Field, we're going to fly to Melksham, pick up the river,
Yes.
fly along the river over the Nestle factory and the weir there, and then to Bradford and Avon, where the project is.
People have lived in this part of the country for thousands of years, and right up to the invention of the steam engine, their only source of power, apart from the horse, was water. Over there is the site of the Avon rubber factory in Wiltshire, and that is part of our story, and I will come back to that and tell you a bit more later. Hundreds of mills were built along the Avon, and we are now flying along the river to see the site of the new turbine at Kingston Mill. We are now approaching Bradford-on-Avon and the Kingston Mill, which is part of the Hall estate. There is a very interesting engineering connection with the Hall estate. Records show that the mill was originally used for grinding corn back in the Saxon times. It then became a woolen mill. It closed after the wool trade moved north during the Industrial Revolution, when steam became the principal source of power. The mill remained idle until 1848, when the engineer, Stephen Moulton, bought the Hall estate to establish a rubber factory to produce vulcanised rubber. Moulton was a contemporary of the great Isambard Kingdom Brunel and did produce rubber fittings for Brunel's ship, the Great Eastern, at the time the largest ship in the world. The factory went on to produce the first pneumatic tyres for the new motor car industry. This magnificent Jacobean mansion is the Hall estate, home to the Moulton family. Great engineering continued here. Dr. Alex Moulton, who is the guy that invented the suspension for the iconic Mini. The most popular car that was ever built in the UK, with over 5 million of them made, with a suspension system that was designed right here. Alex also designed the Moulton folding bicycle, which is still in production now. The Avon Rubber Company has now moved and is in Melksham and Westbury, but it is still producing many rubber components for many types of industry. The trustees of the Hall estate are keen to keep engineering alive by encouraging young, innovative engineers. I'm now going to Devizes to meet Martin Tarrant, who is the engineer that's built this turbine. Well, I can't wait to see this propeller because from the other end it's looking mighty impressive. And this is it?
Yeah.
Wow. Okay, so I can see there where the propeller mounts, where each of the blades mounts on the central hub.
Yeah.
And this must fit into, do you call it a quartz ring or?
The propeller on hydro turbines is called the runner.
Yeah.
Each blade is then mounted on a hard chrome stainless steel shaft.
Okay.
That runs in composite bearings, basically.
Right. So that can cope with all of the underwater side of stuff without giving any trouble.
Yeah.
Right, so Martin, I've got to ask, I can see that this is a very, very complicated propeller. I can see that there's a variable pitch on it. I can see that it's going to have to fit into a very tight-fitting ring to make it work.
Yeah.
But I'd love it if you just explain it to me in a sort of almost idiot-proof fashion, because there's a lot going on here.
Yeah. It's basically just a variable pitch propeller, as you would have on a larger ship, apart from the profiles of the blades, where we're after as much coverage as possible to pull as much energy from the water as possible.
So when you're talking about that coverage as possible, as much coverage as possible, you're talking about the fact that these blades cover pretty much 100% of the surface area. So when they're in their flattest position like that, almost neutral position, very little water can squeeze past these through these gaps. So any amount of pitch that I then put onto this, it'll let more water through and spin much faster. And the pitch is operated inside here.
Yes.
So can I turn this?
No, you won't turn it.
Right.
There's so much drag on the seals.
Right. But if I were to turn this, would it push this plate backwards and forwards?
There is a plate that goes on there. It's not on there at the moment with a push rod, and it's actuated from inside.
And that comes through this and attaches to these rose joints.
That's it. Yeah.
I see. I get it.
Yeah.
So that's just the central boss.
That's it. Yeah.
And a push rod comes in and out of here to push these rose joints backwards and forwards and give each blade its correct pitch.
Yeah.
And they're all linked together as one, working as one.
Like one driver blade.
Yeah, I see. And this is a hell of a casting as well.
Yeah.
How long has it taken to design this lot?
It's been an ongoing project really for several years really.
Who was the original sort of idea person behind this?
That was myself. The original idea was I was going to build one for myself. I had a mill over at Avon, which I've subsequently sold. So the original idea was to build a turbine for my own use.
Okay.
But since then it's had several people shown interest in having turbines built in this country.
There are a surprising amount of turbines in this country, aren't there?
Yeah.
And a lot of water wheels as well.
Yeah,
I mean, just in this local area, I know of 5 or 6 that I've been to or visited or just know of.
Yeah.
And that's just in the immediate area.
Yeah.
So people also sort of seem to think that water wheels, water turbines and stuff like that are a thing of the past and all been decommissioned.
Yeah.
But that's not the case, is it?
No, it's there's quite a few in the area, but there should be a lot more. If you look at the River Avon, virtually every mile and a half, there's a weir.
Yeah.
Wherever there was a weir, going back to the Saxons, they used it for power. We seem to have forgotten how to do this.
Yeah, which is a pity, isn't it?
Yeah.
But this type of machine is ideally suited to that very low amount of fall, of head.
Yeah. It's the most efficient for low head sites. Like I say, this will run down to 80 litres a second and still maintaining 80% efficiency at those low flows with a peak efficiency of over 90%. So it's the most complex that you can come up with. But when it comes to optimizing a river, it's on lowland low head sites, it's the best option.
Yeah, it seems ideal.
Yeah.
But it's a far cry from the old-fashioned Victorian turbine, isn't it?
Yeah.
Which is a very basic, very crude box with some plates in the bottom that just lets it go whiz, and there you go.
The mill I had, that was fitted with a 54-inch Armfield turbine. Very efficient at high flows, but at low flows, rubbish because you just cannot adjust it. It's you're trying to maintain 100 RPM, and you're just going to lose power trying to do it with
which is where this comes into play, isn't it?
Yeah.
So this is an all-round winner then.
Yeah.
I'm really in awe of the whole thing. I think it's amazing, and the level of engineering in the whole thing, through the plate work, through the machined parts, through the castings, through the intricate parts on the inside. I mean, this thing is the the nuts, really. Can we have a look more at the what we call the wickets?
Yeah,
see how those work.
Yeah,
because I can see where they mount.
Yeah.
Wow, Martin, this is one hell of a construction. So this is the inlet.
Yeah, we can feed up to 6 cubic meters a second through this.
That's an awful lot, isn't it?
Yeah.
That is an awful lot. Yeah, and considering your aperture at that end is not particularly massive.
It's with the centre of the propeller. We're looking at 1 square metre.
Right, well, I'm keen to see where these wickets actually go then, Martin. This must be it here.
Yeah.
And this must be one of the wickets.
It is.
So how does that fit into there?
There's a shaft on one end. I'll just get one.
Okay. I see.
So that's the inner shaft, which goes in there. And that's a bearing in that cup that sits in this end.
I get it. So when those 3 components are welded together, from the inside you can get your wicket, put it into that far hole, line it up to this one, and then that bearing cup there.
Yeah, there's a plate on there with a spigot that goes into the bearing cup.
So these are all controlled from inside the main body.
They are, yeah.
On the axle end.
Yeah. There's a lever.
Plates with a lever.
Yeah.
In a similar sort of arrangement with a push rod to change
That's it,
the
round
pitch of the
ball
whole
ring.
thing.
Yeah.
And the whole ring turns.
That's it.
Let me get
So
it.
one
Okay.
hydraulic round.
So we've got a series of axles coming in,
Yeah.
and then to one side of those we've got a ring,
Yeah.
and off each axle there's a rod
That's it.
that goes to the ring. You turn the ring,
Yeah.
rod
Moves
gets
all-
pushed,
Yeah. Moves all 20
wicket
the same. Yeah.
turns around, and they all
Yeah.
close and open
That's it.
together. Wow. So when those are closed, you can pretty much close the water off to nothing.
Yeah.
And
They,
when they're
they,
open
they
full-
touch full length. They even touch on the casing.
So really it's sort of thinking into the future as well.
Yeah. Yeah. It's,
But bearing in mind, it's going to take many years to wear out.
oh yeah.
So
Yeah. It's
you have got to think about these things, haven't you?
Yeah.
And what sort of steel is this? What sort of grade level of steel is this?
It's just S275 standard.
Well, that's just standard,
Yeah.
normal but high
Yeah.
quality
That's
mild
it.
steel.
Yeah.
That's what you build. That's what ships are made from.
Yeah,
That's
that's
what I
it.
make my Dutch barges from.
Yeah.
Yeah.
So
Yeah. So it's not core 10. But
No.
that'll be Lloyd's rated though, won't it?
yeah. It's all commercial steel.
So I would presume that all of these are high quality stainless steel.
Yeah.
316.
That's it. Yeah.
Yeah, nice. And these axles here, they must also be stainless.
They are. Yeah.
So, this is my question. How are we going to weld this piece of stainless steel to that piece of mild steel?
Using a 309 stainless steel filler wire.
Okay, so that's 316.
Yeah.
The filler wire is going to be 309.
Yeah.
And how does that make it better? Because I know there's normally problems.
The problem is migration of carbon into the weld, and the 309 stainless eliminates that pretty well. So.
Yes, because that's the problem. Normally you get this sort of edge where the stainless goes to the mild, you get this fracture line, this brittle part.
That's it.
But using the 309, you don't get that problem, and you get a clear, nice welded section.
Yeah.
Wow. Well, that's going to be interesting. I want to see it when we get to that bit as well.
Yeah.
So this is the inside axle for the
Yeah.
wicket back. That goes onto the inside bearing
Yeah.
down there. That's where the bearing and seal is, I presume.
Yeah.
And then this piece here is where the
Lever is
attached to rotate
Yeah.
the wickets to open them all
That's
or
it.
close them.
Yeah.
And the leading edge,
Leading edge is there.
and this one that's been tapered is the run-off edge.
Yeah, it's a trailing edge.
Is that to cut down on resistance and
Cut
noise?
down on turbulence from the trailing edge.
Yeah.
Basically.
So the leading edge is pretty much a rounded bull nose.
Yeah.
And then this one tapered off
Yeah.
on the, I'm trying to work out which side it'd be done on, but then that, as it exits the bit of water that it's cut through,
Yeah.
the water's allowed to come back together
That's
nice
it.
and cleanly.
Yeah. Yeah.
Does that cut down on noise and vibration then?
It does, but it's the weight of this noise and vibration is not too much of an issue.
Right.
The generator being inside, that's got a meter of water all the way around it as well. Generators.
It's almost water silenced, isn't it?
Yeah.
Yeah.
So the generator is also liquid cooled, so there's no fan on it, so you don't suffer with noise from fan. Most of the noise on an electric motor or generator is fan noise.
Is it?
But because we've got a certain amount of energy to lose via heat.
Yes.
The generator itself is water cooled.
And I suppose because it's inside that casing,
Yeah.
then being water cooled,
Yeah.
means that the whole inside of that casing doesn't get overheated.
No. The gearbox, we've got no cooling on that, but it's less than 2% loss through the gearbox. So even on 55 kilowatt, we've only got a kilowatt to lose. So
Yes.
the casing itself will lose that heat.
So you're talking about the internal casing that
Yeah.
the generator goes in.
Yeah.
That'll sink some of the heat
Yeah,
out into the
that's
water.
it, yeah.
And then you've got a water
Yeah.
system pumping around the generator
Yeah.
to lose heat from that.
Yeah.
So that it just becomes a lot more efficient, keeps
Yeah.
the whole thing cool.
So with the generator, if it was an air-cooled generator, then we're looking sort of 95% efficient. So we'd have 2.5, 3 kilowatt to lose off of that.
Right.
So we've water-cooled that's what we call the jacket that this blade runs in. Is actually a heat sink as well.
Is it?
So the
Okay.
coolant from the generator is pumped around the heat sink, which has got water flowing through it, and the bottom half of it is submerged as well.
Okay.
So
I mean, this is by far the most technical generator I've ever seen.
Now, Martin, what is this?
draft tube for the hydro turbine for Bradford on Avon.
So this is where the water comes out after it's been through the turbine? So why is it so big? Why isn't it just a one pipe coming out?
The draft tube increases in size as it progresses downstream, which creates a suction on the turbine. Assists basically the flow through the turbine.
Okay.
So it's if it was the discharging straight from the runner, you get a large power loss.
Okay. And will this be underwater or will it be tipping into the stream?
No, the end of it is submerged all the time. At the lowest flows in the river and the lowest river level, the end of it is still half a metre below the lowest water level.
So you won't see it?
No.
Okay. So where's it going now? Now it's on the truck.
Going down to Global Coatings in Bristol to be painted, and then from there straight to the site.
And is this a special paint? What are they?
Yeah, they're using a 2-pack epoxy paint, which is similar stuff they use on sort of oil rigs and
submarines and things like that.
Yeah.
Good. Okay. So you have to repaint it. How long will the paint last?
Manufacturers guarantee 25 years minimum on the paint, so providing there's no damage to it, so I shouldn't have to worry about it for a while.
It is installation day and everything has come together. The site has been prepared, the turbine is finished and the crane is here. A long reach crane is needed for this job. Just getting a truck this size through the narrow streets of Bradford on Avon has been a challenge, and the crane has to be this size to be able to reach across the water. You can see the Hall estate over the fence in the background. Martin is having a moment. He's just wondering if it's all going to fit. That's got the turbine in. Now for the draft tube. This has to be inch perfect. This is a very complex bit of kit, and it's great to see it's been designed and built right here in Wiltshire. And it just goes to show what we can do if we have a go. All functions of the turbine can be monitored remotely, and Rupert can log in wherever he is. The specialist software had to be written to convert DC current to AC current and then match the phase and the peak demand required by the grid. The software to manage the system has been written by Richard Armstrong of Rytec. All my life I've had a passion for engineering and seeing how things work. It's been a real pleasure to have an overview of this project and see the detail of the design and the manufacture, the welding, the milling, the fabrication. It is just incredible, and it's really nice to know that it's all been done right here in Wiltshire. Rupert and Martin should be very pleased with what they've achieved. This new turbine should last for many, many years, and with the history of Bradford on Avon being what it is, where the water has been used as a power source in the past, the river is again producing power, just like it did in the past.